Today we start how to find Jacobian for implicit functions. Jacobian for implicit functions. Is it okay? So yesterday we learned the definition of Jacobian for two functions, two independent variables, three functions, three independent variables, four functions, four independent variables. But that was the case for explicit function representation. So now how to find the Jacobian of two functions with respect to two independent variables whenever they are given in a implicit form. So let me have two functions u and v, u depending upon xy and v depending upon xy, and there are given two implicit relations between u, v, x and y, that is f1 u comma v comma x comma y is equal to 0 and f2 u comma v comma x comma y is equal to 0. So we are given two implicit functions f1 and f2, and of course they are depending upon u, v, x and y. So now let me differentiate f1 and f2 with respect to x and y in a partial manner. So differentiate with respect to x and y. So you will get del f1 over del x plus. Now u and v are functions of x and y. So here you will apply the chain rule. You will get del f1 over del u into del u over del x and plus del f1 over del v into del v over del x, and the value will be equal to 0. Is it okay? And of course del f1 over del y, this will be equal to del f1 over del y into del u over del y, this will be del f1 over del u and plus del f1 over del v into del v over del y is equal to 0. So in this way I get two equations from functional relationship f1. Similarly I can have for f2, right? So the equations will be del f2 over del x plus del f2 over del u into del u over del x plus del f2 over del v into del v over del x. This is again equal to 0, as well as del f2 over del y plus del f2 over del u into del u over del y and plus del f2 over del v into del v over del y is equal to 0. So in this way I get four equations 2 year and a 2 year. So now what is my requirement? I need to find the Jacobian of uv with respect to x and y. From definition, what is Jacobian of uv with respect to xy? What is that? What is that? Determinant del u over del x, del u over del y. Then determinant del v over del x, del v over del y. It means I need to find del u over del x, del u over del y, del u over del y, and del v over del y. Right? So here I am having 4 equations, and let me treat del u over del x, del v over del x, del u over del y, and del v over del y as unknowns, right? And applying Kramer's rule for linear equations, I can find the expression for del u over del x, del v over del x, del u over del y, and then del v over del y. And when these partial derivatives are found, the Jacobian can be easily found. Is it okay? Clear? So now first let me explain what is Kramer's rule for linear equations. Is it okay? So keeping your expression in your notebook, first let me have Kramer's rule. What is Kramer's rule? Let me say, if I am having 2 linear equations, that is a1x plus b1y is equal to c1, a2x plus b2y is equal to c2. So in matrix form, I may write down it as a1, b1, a2, b2 into xy is equal to c1 and c2. Okay. Now if capital D is a determinant a1 b1 a2 b2 and dx is the determinant, the coefficients of x, this column is replaced with a c1 and a c2. So this is c1, c2, b1, b2. Determinant dy. Now the column of b1 and b2, that is coefficients of y. Now it is replaced with c1 and c2. So this is a1, a2, c1 and c2. So then the solution is given by, from Kramer's rule, x is equal to dx divided by d and y is equal to dy divided by d. Is it clear? Then this is the Kramer's rule. The same rule we shall apply to find out the solutions for del u over del x, del v over del x, and then del u over del y and del v over del y. Right? So just tell me the first equation and third equation. What is that? First equation, I think it must be del f1 over del x plus
del f1 upon
del f1 over del u into del u over del x and plus
del f1
upon del b into del b over del x is equal to 0. And the third equation is del f2 over del x and plus del f2 over del u into del u over del x plus del f2 upon del b into del b over del x is equal to 0. Now I will treat del u over del x and del b over del x as unknowns for these two equations, right? So applying Kramer's rule, what will be the expression for del u over del x? This is equal to minus, because whenever you will be having del f1 over del x and del f2 over del x, to the right hand side the minus sign will be carried. Is it okay? Right? Now in the denominator, in Kramer's rule, that was the determinant of coefficient matrix. So here you will be having a determinant with the coefficients of del u over del x and del b over del x. So this will be del f1 over del u, okay, and then del f2 over del u, and here del f1 over del b and del f2 over del. The determinant of the coefficient matrix, right? And then corresponding to the column vector of del u over del x, that will be replaced by del f1 over del x and del f2 over del x. Is it okay? So here in numerator, the coefficient of del u over del x are del f1 over del u, del f2 over del u, del f1 over del u, del f2 over del u. So this column will be replaced by del f1 over del x and del f2 over del x, and this will remain the same, del f1 over del v and del f2 over del v. Is it clear? Now what is this? This is the Jacobian of f1 and f2 with respect to x and v. And what is this? This is Jacobian of f1 and f2 with respect to u and v. So this can be written as is equal to minus Jacobian of f1 and f2 with respect to x and v, and divided by Jacobian of f1 f2 with respect to u comma v. So in this way you get the expression for del u over del x, right? Again, what do we need to find now? Del v over del x, expression for del v over del x, right? Now go for the expression for del v over del x. Of course, minus sign here. The same thing will remain in the denominator, that is the coefficient matrix of del u over del x and del v over del x, right? So this will remain the same. del f1 over del u, and then del f1 over del v, del f2 over del u, and del f2 over del v. Now here in this denominator, the column vector with respect to the coefficient of del v over del x, that will be replaced by del f1 over del x and del f2 over del x. Here it means that this column vector is now replaced with the del f1 over del x and del f2 over del x. This will remain the same, del f1 over del u and del f2 over del u. Now this determinant is nothing but the Jacobian of f1 and f2 with respect to u and x. There it was with respect to x and v. Here it will be with respect to u and x. So this will be equal to minus Jacobian of f1 and f2 with respect to u and x, and divided by Jacobian of f1 and f2 with respect to u and v. So in this way I get the expression for del u over del x and del v over del x. Is it okay? Similarly, I can find out the expressions for del u over del y and del v over del y. So all four partial derivatives can be found in this way. Is it okay? So let us go for del u over del y and del v over del y with equation number 2 and equation number 4. Okay? So now what is equation number 2? That is del f1 over del y plus del f1 over del u and del u over del y plus del f1 over del v into del v over del y. This is equal to 0. Fourth is del f2 over del y plus del f2 over del u to del u over del y and plus del f2 over del v into del v over del y. And as we did for the partial derivative with respect to x, I can find a similar type of expression with respect to y as well. Okay. So what was there for del u over del x? What was there for del u over del x? That is minus Jacobian of f1 f2 with respect to x and v. So now this will be with respect to y and v. So del u over del y, this will be equal to minus Jacobian of f1 and f2 with respect to tell me
y or v.
Y and v. And then again Jacobian of f1 f2 with respect to u and v, right? And del v over del y, this will be equal to minus Jacobian of f1 and f2 with respect to u and y, and divided by Jacobian of f1 f2 with respect to u and v. So these are very simple formulas. You can memorize it if you are given two implicit functions between u, v, x and y. Two relations f1 and f2, let me say. Is it okay? So I can have an expression for del u over del x. What will be that? The Jacobian of f1 f2 with respect to x and v divided by Jacobian of f1 f2 with respect to u and v. Everywhere the denominator is going to be the same. What is changing? Only numerator. So for del u over del x, that will be the Jacobian of same f1 and f2 with respect to u and x. Is it okay? Then for del u over del y, numerator Jacobian of f1 f2 with respect to y and v, and then del v over del y, Jacobian of f1 f2 with respect to u and y. Is it clear? The denominator is always the same, Jacobian of f1 f2 with respect to u and v. Only what is changing in the numerator, Jacobian of f1 f2, that is same, but with respect to different combinations. First, for x it will be y and u. Sorry, for x it will be x and v. Sorry, for x this will be x and v. For del u over del x. Similarly, for del v over del x, it will be with respect to u and x. If you are having the partial derivative with respect to x, then the combination of x, u and v. If you are having partial derivative with respect to y, there will be the combination of u, v and y. First with respect to y and v, and then with respect to u and y. Right? Is it okay? Fine? Clear? So this is all about to find out the Jacobian for implicit functions. You need to find all four partial derivatives u, v with respect to x and y. The way I have explained here, how to find those partial derivatives. When the partial derivatives are found, the Jacobian can be easily found. Clear? So second implication of the Jacobian. What will happen? The question is that the topic is functional dependence. Functional dependence. I am given two functions u and v with respect to x and y. U is equal to uxy, v is equal to vxy. Is there any relationship, functional relationship between u and v? This is the question, whether it is yes or whether it is no. This will be given with the help of the Jacobian. How? Let me explain. The question is, what is the question? Whether a relationship between u and v exists or not. Okay? Let me say there is a functional relationship between u and v denoted by capital F. Okay? So there is a relationship between u and v. Fine? Now what should I do? Let me differentiate it with respect to x and y partially. Okay? So what will happen? That will be del f over del x plus del f over del u into del u over del x plus del f over del v into del v over del x is equal to 0. But you can see here there is no dependence of capital F on x and y. Is it clear? So the value of del f over del x will be equal to 0 because there is no x, there is only u and v. So this term will be 0. So I shall have now del f over del u into del u over del x plus del f over del v into del v over del x is equal to 0. Is it okay? Because f does not have x, so there is no appearance of x, there is no dependence of capital F on x and y. That's why del f over del x and del f over del y will be equal to 0. Is it clear to all of you? Right? So similarly, when I shall differentiate it with respect to y, I shall get del f over del u into del u over del y plus del f over del v into del v over del y is equal to 0. Now what was my problem? Whether f exists or not. If f exists, there will be, depending upon u and v, if there is a relationship between u and v, it is my question. If there is some f depending upon u and v, that is capital F u comma v is equal to 0, then del f over del u and del f over del v, they will be definitely non-zero. Right? There is some expression u and involving u and v. Whenever I shall differentiate partially with respect to u and v, I shall get some expression or not? I shall get some expression. Definitely that will not always be 0. So for non-trivial solution or non-zero solution for del f over del u and del f over del v, what should happen then? The coefficient matrix and its determinant should be equal to 0. The result is from homogeneous linear algebraic equations. If you are having two equations, a1x plus b1y is equal to 0, a2x plus b2y is equal to 0, and if you want to have non-zero solution or non-trivial solution for x and y, the determinant of coefficient matrix, that is a1 b1 a2 b2, that should be equal to 0. Only then you can have some non-zero solution. It is a result from the system of linear equation. So then what will happen? The coefficient matrix and its determinant will be equal to 0. So for non-zero, del f over del u and del f over del v, the determinant del u over del x and del u over del y and del v over del x and del v over del y, this determinant will be equal to 0. And what is this? This is nothing but Jacobian of uv with respect to x and y, that is equal to 0. So if I am given two functions u and v depending upon x and y, and there is a question, is there any functional dependence between them, find out the value of the Jacobian of uv with respect to x and y. If the value of that Jacobian is 0, you will say yes, there is a relationship. If this is not equal to 0, then there is a no relationship. Clear? So these are few applications of the Jacobian. We can have problems, we can solve the problems. Is it okay? So this is all about the applications of Jacobian for our course, for our target. Is that clear? So we stop here.